Hey everybody, Neil deGrasse Tyson here. We recently posted a short 10-minute maybe explainer video on what nuclear fusion is and why it matters for the future of energy. And it basically went viral for us. Had a couple of million views in a relatively short amount of time. And we read the comments and people said, give us more. We want to learn more about this than what I could possibly squeeze into 10 minutes. So we heeded your advice. We do read the comments, and we've put together an entire show on that very subject. And who do we get for it? The operations manager at the National Ignition Facility of Lawrence Livermore National Labs. He's a physicist, and his name is Bruno Van Wonterghem. And we have an entire show with him as our guest, telling us about what they achieved, how they achieved it, and what it means for the future of civilization. So I present to you the show that all of you called for on StarTalk. This is StarTalk. Today, we're going to talk about fusion and lasers. Ooh, co-host Chuck Nice. How you doing, man?
Hey, Neil. How are you?
Man, fusion and lasers been in all the news. Who would have thought?
It is the hottest thing going. Okay.
I see what you did there.
Oh, God. I'm so sorry.
and we did a little explainer video, and I got people comfortable with what was going on at the Lawrence Livermore Labs.
Yeah.
But we thought, why don't we just get somebody from the labs? I mean,
okay.
Why not?
That sounds good.
So allow me to introduce you and our audience to our special guest, Dr. Bruno Van Wonterghem from the National Ignition Facility at the Lawrence Livermore National Labs. Bruno, welcome to StarTalk.
All right, my pleasure.
Okay, excellent. And
Bruno, you definitely are. You have to be Dutch.
Are you feeling it?
Yeah.
Okay.
You know why?
Yes.
Yeah, that was such a Dutch answer. Like, you know what I mean? All right. Okay.
Yeah. That's how we react to it.
That's how you do it.
I'm serious. That's
so
great.
right now you are
I'm acting director of the National Ignition Facility, and I am also operations manager for the facility. So I basically keep my pulse on everything that is happening in the facility, make sure that the experiments are done well and done effectively and safely, and make sure that we get the great results going. Mm-hmm.
In America, we call that boss man.
Yes, that's how everyone thinks about me. Yes.
Yeah.
boss man.
You're the boss man.
I'm the man that's in charge. Yeah, I got my hand on everything.
So, in your past, you have a PhD in chemical physics from the University of Leuven in Belgium. Is that correct?
Yes. Mm-hmm.
Excellent.
Yes.
And your background is in basically lasers, which is so cool.
It's always been about lasers. And as I started out, I was working with, of course, much smaller lasers. But I got my eyes on what was going on in the world, in other laboratories. And so in the 1980s, I moved over for a postdoc at the University of California in Irvine, again, working on lasers and X-ray sources and very interesting projects with respect to laser physics. Then I moved to work for a couple of years at the Max Planck Institute in Göttingen in Germany.
And just remind me, the Max Planck Institute is many different centers that each have an emphasis, correct? Because we have one in astrophysics, but that's not the same one you're describing, correct?
That's unique. So I was working in the one that was focusing on biophysical chemistry and using lasers, to develop all kinds of diagnostic techniques. And actually it evolved into a laser production center. It was studying, extremely high power excimer lasers, a different type of technology. But again, it was, the biggest excimer or the highest power excimer laser under development in the world at that point in time. And that's how I met a visiting scientist from Livermore, explaining about fusion technology, explaining about the Nova laser that was in operation at that time at Livermore, and basically putting a picture of a Nova laser beam on the whiteboard, which was about, year big. And that convinced me immediately to say, well, that's the place, that's where I belong.
So like I said, we posted a short 10-minute sort of update after the news hit. And in the comment thread of our just little 10-minute update, there are a bunch of questions we want to sort of bring into this much more full and fleshed out program. And so there's an unlimited number of these questions. We culled them. And so could you just tell us, first of all, the National Ignition Facility, when we think of ignition, we think of turning on our car. So when you say ignition, what do you mean?
An igniting plasma is basically a plasma that heats itself up higher and higher. And so the heat that is generated is larger than the energy losses. You lose energy from a reaction, through radiation, through conduction of energy away from the plasma. But if you can generate so much heat that you overcome those losses, then you keep heating up, you keep accelerating the fusion reactions, and basically it becomes a runaway reaction, and it's like a match that you light up, where you start slow and suddenly it flares up and it burns up immediately. And so an igniting plasma is a plasma that sustains itself and heats itself up higher and higher. So you get more fusion, you get more ignition, you get more heat production, and basically, whoosh, you basically burn all the fuel that you have collected and compressed around that little hot spot that ignites the plasma. So we call that hotspot ignition. Mm-hmm.
I'd like your reference to the striking of a match, because, of course, when you start out with a match and a little, rough surface, there is no heat anywhere, right? And so then you strike it, and then you start something, and it doesn't need you to keep helping it. It just is self-sustained as it continues.
Yes, it takes off by itself, and it goes faster and faster, and it actually is over in just, a tenth of a billionth of a second. And that's the amazing thing, is you create this enormous amount of energy through the fusion process, and it is basically released from a tiny little spot in an incredibly short amount of time. So the amount of power that is generated is just incredible, and it shows the power of fusion, really.
Wait, but from the notes I saw, you invested, is it 300 million joules of energy? That yes. Seems like a high starting point.
It's a lot of bling. That's a lot of bling.
Yeah. It's a lot of energy, but what we're comparing, or the official definition of target gain, is comparing the energy we put into the target to the energy that came out of the target. Mm-hmm. Right,
and so even if 300 million is a big number.
Yeah, 300 million joules is a lot of energy, but we also have to keep in mind that the National Ignition Facility was never built for efficiency. It was built for cost effectiveness. And so we choose, the most inexpensive power supplies, the most reliable laser systems, and it worked. It was cost effective, but it wasn't, built for efficiency, and could have built a system with an efficiency that is 10 to 50% or 10 to 50 times higher if we would like, to do that. So yes, it is a big number, but it's no surprise, and you also can look at it over time.
What you're saying is you put in 300 million joules, you got out more than 300 million joules, but not much more. And what you're telling me, if I understand, is this was a test of concept. Now that it works, you could go back in and say, let's make this laser a little more efficient. And this, so you can ignite it in principle with fewer than 300 million joules in a new design in the future.
Yes. So So let's repeat that. So we had 300 megajoules of electrical energy that's converted to 3 million joules of laser energy, which is then, 2 million joules of laser energy, which was incident on the target and compressed the target. And then the target itself emitted 3 million joules again. So we had from that point of view, a 1% return, but a 50% relative to the laser energy that was used to, push the fuel capsule together and ignite it.
Wait. So you needed energy to power the lasers.
Yes. Mm-hmm.
Okay. But you're not counting that in the return on the investment, though. You're only comparing your laser energy to what came out of your pellet. But the fact that you had to plug all this into the wall.
Yeah, of course.
So is that fair? Is it fair to think of it that way then?
It is fair, but once you start to think about now, how can we, turn this into a process that delivers energy and can create or use the fusion process, to drive a power plant, then of course that efficiency of the driver becomes very important. You need to start working on higher gain targets. You need to start working on higher efficiency laser drivers. And these two in combination, can basically deliver to, a feasible inertial fusion energy plant.
Okay, so it's engineering at that point. You're going to hand it over to the engineers and say, make this work.
So can I ask you this? So you said that it's like striking a match and that it's self-sustaining. Is there a process where we don't have to worry about how much energy it took to start it because it is self-perpetuating afterwards?
Good question.
Yeah. So the way that
yes, Chuck.
Yeah.
Okay.
Yes, Chuck.
Well, Chuck, there you go. You solved it. Okay, now go home.
Yeah. Actually, the inertial confinement fusion, which is the process that we're using, takes a finite amount of fuel in a little target and compresses it, and then creates fusion in the center to light off the little fuel match around it. But it's a finite amount of fuel, and so once that fuel is burned, we need to start that process over again. So we bring in a new target, we again hit it with a laser, compress it, create the hot spot that ignites it, have the ignition, burn up the fuel, and do it over and over and over again. And so we believe that for a inertial fusion energy plant, you need to do that about 10 times per second, right, instead of once a day. Mm-hmm. And so it's a process that you repeat over and over again. So it's not that we have a gigantic amount of fuel that we can compress. It's a small amount, but it also makes it inherently safe. There is no runaway condition. There's nothing, that basically can melt down or become unsafe from that point of view. The best thing that can happen is that all the fuel burns up.
And that's it. Right. So unlike our current nuclear power plants where, the actual chain reaction can run away and we can't stop it.
Yes, you can have meltdown conditions. You can have all kinds of undesirable effects and very unsafe conditions that can be created, but that is not the case for inertial fusion energy.
So before we go to our first break, could you explain why you need such high temperatures in like the tens, or even, did I read 100 million degrees? What is the temperature doing for you?
So the temperature is needed actually to overcome the repulsive forces that normally prevent the nuclei in atoms from basically combining with each other.
Because they're all positive charges, right? Yeah.
They're all positive charges. So the closer you bring them, they start to repel each other vehemently, which is a good thing because otherwise the whole world would collapse immediately. So there's an incredible force that prevents you from molecules from fusing. And in order to actually then overcome those forces and then have the nuclear force, which is the force that actually pulls the charges together in the core of an atom, you need to have incredible temperatures in order to start creating, violent, collisions between the atoms. So you can relate the temperatures to kinetic energy of the atoms moving around. And if you want to increase that temperature, increase the velocity at which they collide with each other, you need to go to temperatures of about 150 million degrees in order for deuterium and tritium basically to fuse together. And for some other systems, it can go up to billions of degrees before you can actually reach conditions where the nuclei can overcome, the forces that normally prevent them from collapsing.
So presumably this has been some of the decades-long challenge that this process has encountered.
Yeah.
Okay.
From the initial idea that the lab, developed soon after the invention of the laser in 1960s, it has taken us about 60 years, basically, to learn how to do this and learn how to achieve ignition. And that's why the December experiment was such a spectacular event, because it basically, showed us that whatever was deemed impossible for so many years by so many people was basically overcome using just a continuous development of technological and scientific developments in the laboratory, where we develop new codes, new computers, new and bigger laser systems over 60 years to finally come up with a laser and a target design that actually did the trick and worked. And
Bruno, you're talking about rooms full of smart people. Just say it.
It's rooms. It is a campus full of smart people.
Campus
and it's
full
actually
of smart people.
not even one campus. It's multiple campuses across the country, and across the world that have participated in this.
Of course. Bruno, in the center of the sun, it's actually not hot enough to fuse the hydrogen outright. And when we run the calculations, because the center of the sun is like 10 million degrees around there, that it's mostly driven through tunneling, quantum tunneling of the protons to come together. And so you can get the tunneling at the lower temperature. Are you saying that your process going up to 100 million degrees, the brute force slamming together of the protons, that you're not taking advantage of any quantum mechanical tunneling that might be available to you?
There's some amount of tunneling involved, but I think we want to basically, speed up the process, and that's where we try to reach the higher temperatures. Because if you look at the fusion energy production in the sun, it's actually really small. It's on the order of a few hundred watts per cubic meter, which is, almost like the level of a compost pile. So the enormous amount of energy from the sun really comes from the gigantic
just how big
size of the sun.
Just the size of it.
Damn, I've never heard anyone cast shade on the sun before.
Yeah,
and
man,
you did.
You did. You threw shade at the sun. It's just like you're not so hot.
Oh, you're not so.
You're about as hot as a pile of garbage under some dirt, son.
A pile of steaming manure. Yeah, there you
hello,
go.
soul.
And it's a good thing, actually, because if the sun was igniting, that wouldn't be a good day for us. So
of course,
I think
of course.
It's a nice and steady process.
Right,
got it.
Right.
Whereas
so
when you go to the full up temperature that physically gets the protons together without relying on the tunneling, which is a kind of an effect happening in the edges of the process. If you go full up, then you're going to get the full hammer of the nuclear fusion. Okay.
Oh, what a great villain story for a Bond movie. Because Bond movies love lasers, right?
Yeah, they do.
Yeah. So it's like an evil genius who comes up with a laser that he's going to use to ignite the plasma of the sun and destroy the whole solar system. Forget the one where he's just like, I'm going to destroy a city. He's like, I'm going to wipe out the whole solar system.
Mm-hmm.
Okay, that's why you don't have a job at Lawrence Livermore Labs, Chuck. That's why. All right, we're going to take a break. When we come back, we're going to get into lasers and what are they and how do they work and why are they useful for this? And I want to get into a little bit of, dare I say, the chemistry of what's going on in the nuclear reactions? Like, what are the nuclei that are actually coming together, and where do you start and where do you end? So we'll get into that when we return on this edition of StarTalk. We're talking about lasers and fusion. We'll be right back. We're back. StarTalk. We're talking about lasers and fusion. And of course, the person powering this conversation is Bruno Van Wonterghem, who is the acting director of the National Ignition Facility at Lawrence Livermore National Labs. And Bruno, so before we get on to just what lasers are and how they work and why, just remind me what particles are you putting together in what sequence before you declare that you have completed your fusion path?
So the fusion reaction that we are pursuing is deuterium and tritium being fused together to form a helium atom and a neutron. So the neutron runs away with a good fraction of the energy of the fusion reaction, while the helium is a massive particle that is actually used to heat up the remaining fusion fuel. And in the process of fusion, we convert mass into energy. And based upon Einstein's equation, E equals mc squared, c squared being a gigantic number, a little bit of mass is actually converted into a lot of energy. And you create a more, stable, a little bit less mass, and a lot of energy, and that is what we're trying to harvest in this process.
Wait. So how about the runaway neutron? Where does that go?
Into witness protection.
Witness protection.
Witness protection.
It just goes and scatters around in concrete until it basically finally stops. But it can be harvested using the correct or the appropriate technology and turned into useful energy or turned into electricity or something that
that's what I was wondering, because you can't electrically trap it because it's neutral. So it actually, all of its energy has to just sort of slam into something, and then that energy then becomes heat, I guess, correct?
Yes.
Mm-hmm. So there's a collector. What would it be? I'm so fascinated by this right now. I don't know what to do. My head is swimming. So the byproduct, the neutron. So here it is scattering. Are you saying that you could use some sort of collector and you would be able to gather that?
Yes, it's something like a molten salt mantle around the target chamber that can basically absorb the neutrons and get heated up
and it would heat
carry
up.
the energy away.
Jesus Christ. You could heat up, and that could be used to actually do the traditional way we make energy right now, which is heat water, turn it into steam, and turn a turbine, except that you're not burning anything to create that steam. That is... Do you know that the oil companies are going to kill you, man?
No, stop.
What are you doing? You shouldn't be in public. You should not be in public.
All right.
Yeah. I'm sorry.
We'll embargo this broadcast. Wait. So, but let me get back to this. I know that you can find deuterium in just regular water supply. It was 1 out of 1,000 water molecules has a whatever the number, maybe 1 out of 100, I think, has. Of the hydrogen in the H2O is actually deuterium. Where are you getting your hydrogen that has 2 neutrons, which is the tritium? Where do you come up with that?
Sorry. I'm sorry. You're two physicists talking to each other. Regular person here.
Okay.
Let's get back. Rewind.
No, I got this. Okay. So hydrogen minding its own business.
Yes.
Is 1 proton.
Right.
That's normal hydrogen.
Right.
You can give it a neutron. It's still hydrogen.
That's right.
Except it's a little heavier. We call it heavy hydrogen.
Okay.
Deuterium, so that's 2.
Okay.
You can get a second neutron, cram it in there. Now it has 3 nuclear particles, and that's tritium.
Okay.
But it's still hydrogen.
Okay,
so now that's what's going on here.
That's what's going on. Okay. So now the other thing is 1 in every what molecules now is...
tell me, Bruno, is it 1 in 100 or 1 in 1,000? Somewhere around there?
1 in 5,000 atoms in normal, or seawater is actually a heavy hydrogen or a deuterium atom.
Gotcha.
So it can be extracted, I mean, through chemical techniques, through distillation.
And plus, it's combining, it's making the same molecule as a regular H2O because its chemistry is the same. It's just a heavier hydrogen, right?
Man, I'm telling you right now,
what?
If I had just known all this crap when I was in school, I might not be a comedian right now.
You might have been.
This is amazing.
No, it's fun. It's fun stuff.
It's fun stuff.
So, Bruno, where are you getting the tritium?
The tritium is a much more complicated story because it doesn't occur in a natural process, except at extremely low abundances like 10 minus 18, which is basically non-existent. So our current supply of tritium really is generated as a byproduct in traditional nuclear reactors. For example, one way that it's generated is by you take a deuterium atom and you bombard it with neutrons, like what happens in a nuclear reactor if heavy water is used to cool. Then it creates once in a while a tritium atom, and you can extract that and make it available for use.
Technically, then, it takes energy to make the tritium that's in your reaction. Is that part of your energy budget?
So that's the current process. The process that we would like to pursue for inertial fusion energy is to use the neutrons that are generated in the fusion process to create your own tritium. And you can do that, for example, by bombarding lithium or molten lithium or lithium salt with neutrons. And that creates tritium that can then be extracted from the process. So once you have enough fuel to start, you can start creating, your own fuel.
Right.
Wow.
So once again, self-perpetuate. You're eating the whole carcass. There's nothing left over. We're using it all.
Yes,
that's great.
Okay,
we're using it all.
Okay, so now you get to so you do that. They come together in your high temperature. Now you have helium-3, right? So now we have 2 protons, which is helium, and normally it wants 2 neutrons, but now it only has 1 neutron. So that's helium-3, and you're still not done, correct?
Yeah.
Okay, I guess what I'm asking is, I happen to know, you surely know also, that the solar wind is very rich in helium-3, and helium-3 is heavily embedded in the surface of the moon. And there's been talk of surface mining the helium-3 from the moon, and then injecting that directly into your nuclear fusion, so you don't have to go through the deuterium tritium process before you land on helium-4, the full red-blooded helium. So any thoughts about that?
There is an alternative fusion reaction. The D plus helium-3 can easily also form helium-4, but its threshold of the temperature that is needed in order to start the reaction is higher, almost twice as high as the deuterium and tritium, and not as effective. So we still have a more efficient process with DT than the D helium-3.
Did not know that. Okay. All right.
Yeah, so the deuterium tritium, fusion reaction is really the most effective way of achieving, ignition and operating the system, although many others are pursued. They are much less efficient and much harder to achieve.
So you're saying you don't actually make helium-4. You stop at the helium-3 and you get enough energy and you're happy with that?
Yeah.
Okay. Now let me pivot now to lasers, because all this is empowered by lasers, and this is your bailiwick here. So let's get on the same page here. What's the difference between my PowerPoint laser and 192 lasers you blasted your target with?
The amount of power generated by a typical pointing source is about a few milliwatts. The NIF can generate 500 trillion watts, 500 terawatts on a target, and with an energy of 2 megajoules.
2 million joules,
which is, billions and billions times more than what's typically obtained from a small laser. So it is the world's largest, highest energy and highest powered laser. it contains 192 individual laser beams. Each of these laser beams can go up to, 10 or a little bit more than 10 kilojoules of UV radiation, which is each by itself, the world's largest laser. And so it is a tremendous departure from the typical and the previously used lasers in fusion ignition. It's almost a factor of 60 larger than the nova laser, and similar than other, or the similar factor compared to other lasers in the world. And so it is one of the first lasers that is really engineered instead of being a tabletop large scientific laser. It's a laser that is really designed to be compact, cost effective, high energy, high power, and it is really set up, to meet ignition. And we have worked almost 20 years to bring that laser from initial design in the early 90s to starting the building at the end of the 90s, starting the laser beginning of the 2000s, and completing the laser in 2009 when we started to do actual experiments. So it took us 20 years, to build and put this laser together, and it worked incredible. It's a laser that was just engineered so well that when we brought it up, it all worked and it all met its design requirements, and very quickly it exceeded its design requirements in the way that we currently operate and in the way that we achieved the ignition experiment.
But just to be clear,
December.
Did I hear you say that each of the 192 lasers is itself the most powerful laser in the world? Did you say that?
Mm-hmm.
Wow.
Yes.
So this is the laser that cats actually hate.
The cats.
Yeah.
Yeah.
The cats have
Like,
no.
well, yeah, they don't. They're just like, look at that. We lost another cat, guys. We lost another cat.
Yeah. They have no. Yeah, they have no recourse against this laser. Became a Terminator.
So, but just to be clear, my low power presentation laser, which you dissed, I presume makes a laser beam in the same, using the same physics as your lasers. Isn't that correct? That's correct. Yes. So tell us what that physics is.
So the physics is based upon light amplification by stimulated emission of radiation. So
that sounds like it spells something.
You think?
Yeah. That is exactly what the acronym that was put forward, to describe, the process by which you can actually store energy in molecules and use radiation to actually stimulate or trigger the emission of photons, so that when you do that in a coherent way, in a way where a beam of photons that goes in the same direction with the same wavelength basically creates more photons or more copies of itself, and creates a brighter and brighter beam that goes one direction, that has one color. And that is the difference, between a normal, ordinary incandescent bulb, where you have light that goes all directions over a wide spectrum of wavelengths. The laser beams is a way or means of extracting energy from a medium that you have excited using another energy source, and that could be another laser, that could be a flash lamp, to provide that medium that then can undergo light amplification by the stimulated emission of radiation. And that's the mechanism that is being used to generate the laser beams.
So, as you said, and the design of any given laser only can generate one wavelength of light that comes out. So there's no, you can't tune a laser, I guess. It's only good for that one kind of light that comes out. Is that correct?
That's correct. Though some laser, some gain media or atoms, allow a little bit of tunability around a certain wavelength, but the laser itself is always, is basically characterized by its coherence, and that basically means a narrow spectrum and a narrow spatial distribution of the energies.
All right, so the lasers we're all familiar with use visible light, the red lasers and green lasers, and now we have some blue lasers. But I heard you refer to ultraviolet. So are these UV lasers instead?
The laser itself, the solid state lasers that are used to create the beams and amplify the beams largely use neodymium in a glass media, because we need to be able to handle very high energies and be very efficient at the same time. And they tend to operate in the infrared. So basically, it's a wavelength just above the visible region. It's just a wavelength around 1 micron. Now, the targets don't like the infrared light, because they basically create a plasma and send the laser beam right back towards the laser, which is not a good thing to happen. And so we learned in our previous laser systems that you need to have a shorter wavelength. And we first started to double the frequency of the laser. So we turned infrared to green. And finally, we found that actually converting the lasers, the infrared, to ultraviolet was even much more efficient, because the ultraviolet light can penetrate deeper into the plasma that you're forming. And so it's much better, much more of the energy is absorbed and used for heating the plasma that then can start your fusion reactions.
Wow.
You guys are being very efficient about everything. Just move, and I'm just trying to add up all the smarts that takes. And I'm just very impressed just listening to you talk about this and your in your laserdom that you have there.
Laserdom.
Yes.
Laserdom.
Laserdom. I like it.
We got to take a quick break. When we come back, we're going to talk to our special guest, this acting director of the National Ignition Facility of the Lawrence Livermore National Labs. We're going to ask him about the future of lasers and what's next in line, and when are we going to have Mr. Home Fusion to power our cars, like in the movie Back to the Future? We're going to learn all of that when we return on StarTalk. We're back, StarTalk. We're talking about lasers and fusion with the acting director of the National Ignition Facility at the Lawrence Livermore National Lab, Bruno Van Wonterghem. I think I nailed that one that time.
Yes.
Okay.
You get it.
So, Bruno, I've heard people joke about Lawrence Livermore Labs that those 3 L's really stand for lasers, lasers, and lasers. Is that
Lasers,
fair?
lasers, nothing but lasers.
Yeah.
And from our point of view, that is true.
The lasers are us. Yes.
Yeah. So I remember, looking at the Guinness Book of World Records, tracking who had the most powerful laser in the world. And it always landed at Livermore. So why, yes, you did something great with these most powerful lasers, but over time, why the is it just bragging rights that you have the most powerful laser, or is there some real scientific objective for it?
It was a scientific and technology bootstrapping process, where every time we come up with the design for an igniting target or an igniting experiment, we build a laser, we try the target, and we figured out, well, there was something missing in our understanding. We needed more laser energy and power. There were more energy losses in the process. There were different conditions. And so it took us 5-6 of those cycles since the 70s to figure out a design like the National Ignition Facility, where with high confidence, we said we now have the right recipe, the right number of lasers, the right symmetry, the right precision in the laser to achieve all the conditions that are required to make ignition happen. And it's not all about the size of the lasers too. Equally important is just the quality, the accuracy, and the precision of where you point the beams, where you time the beams, how the power is distributed. because you take a capsule and you compress it 30-fold. So you take a basketball and you turn it into a pea. And if you don't have, exquisite symmetry, you don't get a pea. You get something that just, comes out through your hands.
That's the sound that it makes too.
Yeah. The sound effects as well. Yes, very good.
So you need extremely, high energy, high power, but also extremely precise, extremely stable, extremely well-controlled lasers.
You're creating a perfect implosion.
Right.
Yes.
From all directions out of this sphere. The only value of your lasers is to get the right temperature plasma when you're done. We've also heard of magnetically contained fusion. I guess the tokamak is a whole other possible approach to fusion. How do they get their plasma? Because their plasma is also millions of degrees, right?
Yeah, but their plasma are lower temperature and densities, and they are basically held together using magnets in a large vacuum chamber. So it's a very large plasma that is contained and heated up using an induction process. Mm-hmm. So it's quite different. So it's
they don't use lasers.
Much
they don't use
slower
lasers.
and steady. And lasers are only used for diagnostics, but not to drive the process. So,
and forgive me for some of our viewers and listeners. Could you just tell us what a plasma is? Because I think we were just using it like it's, of course, we know what a plasma is. Typically, most people's understanding of the word comes from blood plasma.
Right.
After you remove the platelets or whatever, and what's left is plasma. So there's medical plasma. So what is physical plasma? Astrophysical plasma.
So, physical plasma is basically a collection of a medium of atoms that has been energized or to such a level that it starts to lose its electrons, and so the electrons and the nuclei start to form a continuum and start to float around each other.
So you have free electrons. So that means it could respond to magnetic fields, whereas a normal gas would not have the reason to.
Yeah.
Mm-hmm.
Okay.
And why did they think this was a good idea for televisions?
Plasma televisions.
Yeah. It's well, now you have lasers television too.
This is true. Which is is sharper than the.
Mm-hmm.
Yeah.
Wait. Isn't the gas inside of neon tubes a plasma, and in fluorescent tubes? Isn't that all plasma?
Yes, because it's very easily ionized, and so it easily forms a plasma
without having to go to very high temperatures. It's just
right.
And that little, you don't see it anymore, but that glow ball.
Yeah, that you put your hands on.
You put your hand on, and you see it's this like glowing gas. Bruno, have you seen these? Mm-hmm. I don't know how they let you out. You know.
Nope. No, we have seen those. We use those.
Do they let you out of the facility? You can see them in malls, you know, in gift shops. Yeah.
Yeah, but there are applications of it. But the plasma also allows to be heated further and further, and so you can create, interesting conditions, and you can start to experiment and have atoms, do interesting, physics for you.
Yeah, and most of the universe is plasma. All stars are plasma,
yes.
And so we're we live with it when we study that.
Mm-hmm.
I just wanted to ask, because as you were talking about the refinement of these lasers over a period of time, but it's always been in service to finding a better way to achieve fusion. In that process, has there been advancements in lasers that we benefit? Like maybe you guys didn't benefit, but we did.
You mean spin-offs en route?
Spin-offs, yeah.
Yeah.
We have had a number of spin-offs that are not directly, coming to your home, although, there were a technique that is being used, for example, to harden turbine blades for jet engines using lasers.
That's important.
That has been commercialized and is used on a relatively wide scale. Mm-hmm. There are applications of diagnostic systems that were developed for laser fusion facilities.
Well, I just wonder, now that the turbine blades are harder, maybe they'll just slice up those ducks.
So and then we can collect them on the back end and make lunch.
So now when a plane flies into flocks of geese or whatever, like Sully did and landed in the Hudson River, I don't know. I'm just
but
kidding.
it helps. It helps for that, but it also makes you feel better when you're flying, that you know the engine is going to survive the flight and not basically start to disassemble somewhere en route. So
I hate it when that happens.
I think it's
ladies and gentlemen, this is your captain. As you can see, we just flew through a flock of geese, and I want to let you know that our in-flight meal today will be duck à l'orange.
No. So
we have to be fast for it.
So Bruno, tell me again, do you think what you have achieved here is scalable? Whatever that word means as I'm using it, I don't know, but scalable so that it can be ported to power stations, or maybe I can have one of these in my garage, or where does this go after what you've done?
Yeah, so this concept can lead to the design of inertial fusion energy-based power plants. Those are fairly large plants because the laser system we're needing is not a small laser system. It is a large facility. I mean, we're talking stadium-sized lasers. We have to do a significant amount of engineering development because we need to run them at 10 times per second instead of 1 time a day. We need to have targets that can be, produced, at the rate of 10 times per second. We need to develop, a system, to capture the energy, produce the tritium fuel that is needed to run it, and then convert the energy, basically to electricity.
But it's that's just engineering at this point. That's not physics.
There's a lot of engineering. There is no.
You got the physics down.
Physics.
Right.
We get the physics down. We still want more, higher gain than what we achieved on the December experiment, but we have ways to do that. We understand how we can achieve that.
Wow.
And so, yes, we believe that, within a decade, 2 decades, we may have, a working model of an inertial fusion energy plant.
And so how about one for my car where I have a Mr. Fusion home device? You just put stuff in the top and then close it down, and then I run. That's my day's fuel. That would be like a portable version of it, right?
So that is a little bit, further or far-fetched from this, because right now the scale of the lasers, or the scale that is required, doesn't lend itself easily, to a very compact system. So, but it doesn't mean that there may be ideas to do this.
Computers used to be the size of entire rooms, factories, just to do simple calculations. And now, we carry it around on our hip. So you think lasers might not be shrinkable in that way?
There are definitely materials that can be made more efficient. There can be drivers that are more efficient. So yes, they will scale. I'm not sure, though, that they will scale large enough to be a tabletop type of device. But then again, I don't want to say no, because again, what we see, like in the development of the cell phone, that was inconceivable 50 years ago.
Right.
To have something in your pocket that tells you where to walk,
right,
and how to drive.
I remember my first GPS device was this large. It was handheld, but it was huge, and its only job was to give me my coordinates as I walked. It was a fun sort of novelty item.
And it didn't work.
No.
Yeah.
And now it's some chip inside of something that's 1/10 the size of what the whole thing did, and it does 100 other things, including make a phone call.
Wow.
So what's in the future at your facility?
Yeah.
So
when can we have guns that go pew, pew?
You want laser? You want laser guns? No.
Yeah. Well, there's actually a significant effort on laser-based, or directed energy weapons. Besides, fusion applications. But in terms of the fusion applications and work that will be done in the National Ignition Facility, we want to achieve, significantly higher gains. This time we obtained 3 megajoule. We would like to obtain 10 megajoule, 50 megajoule, 100 megajoule, and basically improve, the process, improve the physics, improve the quality of the targets, and investigate what needs to be done, and make then the fusion yield, useful, for our stockpile stewardship goals.
So in the mission statement of Lawrence Livermore Lab, if I remember it correctly, it's you are the nation's repository and intellectual center for everything nuke, right? Nuclear energy is you, right? So once you're done doing the fusion thing, and then it gets mass produced or whatever, is there a next project that's still within that mission statement that you'll continue to do?
Well, the next challenge that we're looking at is even higher yields, or yields around 500 megajoule or even a gigajoule, which was always, the goal of what we call the laser microfusion or the laboratory microfusion facility, which would have significant implications and significant benefits in our goal of achieving the safety and reliability of the stockpile. And so that would be, our next step in the laboratory. Well, of course, we will be participating and helping out and working together with private industry in developing inertial fusion energy.
Wow.
Okay, so Chuck, just so you're on the same page as what he just said, okay. Did you hear him say gigajoules?
Yes, I did.
Okay, so a joule is a unit of energy,
right?
And 1 joule per second is by definition a watt,
right?
So if he gets to 1.22 gigawatts, then you can travel through time.
That's it.
Yeah.
This is
go.
That is the secret energy level in Back to the Future.
That's amazing.
No, this has been a delightful conversation, Bruno. And we have not met before. Thank you for taking our call. And if we can put you on speed dial, if you have any new developments, we'll put you back on and we'll see what else. Because we have a very eager, curious, and interested following.
Yes.
And
our listeners are smart.
Okay. All right. No, I'm definitely interested in coming back because there's a lot more to talk about.
We will totally make that happen. All right. Again, great to have you. Our guest has been Bruno Van Wonterghem. Yes. The National Ignition Facility at the Lawrence Livermore National Labs. And he's in charge there. What'd you call him, Chuck?
Boss man.
Boss man. All right. That's the one you want.
Okay, I get that. All right.
Well, you put that on your business card, and then people will treat you a whole other way when you do that. Chuck, always good to have you, man.
Always a pleasure.
Neil deGrasse Tyson here. This has been StarTalk. As always, I bid you to keep looking up.